one object equals the mass of another object, and the acceleration is the same, the force will be equal.
When cars that have the same mass have the same acceleration, they will exert the same force. We've set up an experiment with the white car, the blue car, and the pig to show that if objects have the same mass, the cars, and they have different accelerations, they will exert more force or less force depending on the acceleration. The pig will be what the cars exert their force on. This is where the pig starts, and we'll mark where the pig finishes with each car, and then compare the distances. On your mark, get set, go! White car is the pig this far. This is how far the blue car pushed the pig. The blue car pushed the pig a very small distance, and the white car pushed the pig a larger distance because the white car had more acceleration and therefore more force.
Warning, do not try this at home.
For this next experiment, we're going to demonstrate how the mass will determine the force that an object has when the acceleration is the same. And since all things accelerate the same when the acceleration is due to gravity, mass will determine the force that the object exerts. These are the objects that we're going to be dropping on Warren's toes. The rock. So Warren, how much force did that rock have on your foot?
Am I supposed to explain it in scientific terms?
You
Very
can-
much force.
That'll work. The water balloon.
It's more on the rock, although quite a bit.
The tennis ball pirate duck.
Quite as much as water balloon.
A hollow black ball. So, how much force would you say that ball
Not
had?
a whole lot.
The clear hollow ball.
Not a whole lot of force on that one.
Geez, styrofoam ball.
Squish it.
How much force would you say that one had, Warren?
Not quite a lot.
So, if you compare the rock and the styrofoam ball, what's the different forces?
What do you think?
Well, I think that since the rock has more mass, and they both have the same acceleration, that the rock would have more force. Is that how it was?
Yes, indeed it was.
Alright,
You
here.
are the brainy one.
It's been a hard day's night, and I've been working like a dog. It's been a hard day's night, I should be sleeping like a log. But when I get home to you, I find the things that you do will make me feel alright. You know I work all day to get your money to buy a thing, and it's worth it just to hear you say,
Also, I forgot to mention as my colleague has informed me. Come here. Well, I hope to be the last time.
Warning, do not try
Travis, Julius Sumner Miller, Bolton, Shano Drano Shano, then West. Physics is our business.
And today we'll be doing experiments on Newton's first law.
An object remains at rest until it acted upon an outside force. We need to grab it. An object at rest will stay at rest until acted upon on an outside force. Now the objects at rest are these water bottles, which represent the pins. And that force is this ball.
Yeah, it's 50, aka Ferrari F50. Break it down. I got a lot of living to do before I die.
In motion stays in motion until acted upon by a greater outside force to stop it. Keep on trucking.
Alright, another example is we're going to throw a basketball right here and Dustin's going to catch it. And this is an example of an object in motion stays in motion until acted upon by an outside force. Alright?
Alright, another example is this ball is going to stay at rest until a force of causes foot pushes the ball and moves it. Alright.
Y'all gon' make me lose my mind. Up in here, up in here. Y'all gon' make me go all out. Up in here.
Which one you catch? Which one? Hi. Objects at rest tend to stay at rest until acted upon by an outside greater force.
Dude, you just hit that guy.
You should have been standing there.
Okay. We can say anything we want because we're taking out the sound, right? Okay, go.
Can you take off the sound?
Yeah. Whenever you're ready.
Ready.
Action. Now look up at me like, whoa. Yeah, and then go around the corner.
Tell me when.
Whenever, action. You go after him too. Now you go. His head. There you go. Fall out. Whenever you're ready.
How do you want me to do it?
Just jump off and you can just fall down.
Tell me when.
Go.
There we go.
up there. Just go. Here we go. Let me read. A slide is an inclined plane. If we know the angle of the slide or inclined plane as well as the weight of the person going down the slide, we can calculate the acceleration.
Not wet. Yay, Kara! Okay.
Hello, I'm Brandon Jevin, and this is my cameraman and fellow scientist, Manon Zeres. Go.
Good evening, I'm Alan Zeres.
Our project is over energy in the stored sense and transferred energy. We will be using Newton's second law of motion, which states the acceleration of a body is directly proportional to the net force on it and inversely proportional to its mass.
Our first experiment will be using the transfer of energy on a pool table. The acceleration of the cue ball depends on the mass of the cue ball and the force applied to it. In this experiment, the cue stick will be used to push the cue ball into another ball. The ball on the opposite of the table has a huge amount of stored energy, or inertia. We will push the cue ball directly into the ball with such force that the cue ball will lose all acceleration and all energy will transfer to the other ball. Watch it now! Watch it now! Watch it now! Watch it now! Watch it now!
Watch it, watch it, watch it, watch it, watch it.
As they drag you by your feet, but the hangman isn't hanging, and they put you on the street. Yeah, you go back, Jack, do it again. Wheel turning round and round. You go back, Jack, do it again. When you know she's no high climber, then you find your only friend in a room with your two-timer, and you're sure you're near the end. Then you love a little wild one, and she brings you only sorrow. All the time you know she's smiling, you'll be on your knees tomorrow. Yeah, you go back, Jack, do it again. Wheel turning round and round. You go back, Jack, do it again.
There it is, there it is, there it is, there it is, there it is.
Our second experiment will also include pool balls. Using spherical pool balls, if the point of contact is not directly on, then the energy transferred will not be completely lost in the cue ball.
If the ball is hit to the side, it will accelerate. However, the cue ball will not lose all of it.
Let's say hypothetically that the cue ball is traveling at 3 meters per second. After the collision, the energy of both balls should equal the same amount that we originally started with.
This is called momentum. Watch it now.
Watch it.
Stay.
Now you swear and kick in Vegas that you're not a gambling man. Then you'll find you're back in Vegas with a handle in your hand. Your bad car.
Welcome to the Thermal Energy Show with your host, Professor Dr. Fucking Ma, and his seductive sex mistress, La Ridgely. Enjoy the show.
And welcome to the Blah Ragely and Dr. Foggett Moth Show. Today we'll be discussing thermal energy. We will be showing you many examples of thermal energy in action. Our first one is this here heater. This heater is giving off much thermal energy, thereby making us warm. We absorb its thermal energy and we become warm. Now, for our first thermal energy experiment. For this, I will be needing a candle. Mr. Ragely, the candle, please. Over here. Bring the candle over here. Hey, bring the candle over here.
Thank you, Mr. Ragely.
Okay. Now, as you can see, the candle right now has no thermal energy, so I can touch it like this. Nothing happens. I'm not absorbing any thermal energy. Go away. But if I add some flame to it, now the candle is giving off much thermal energy. It's very hot. Don't touch it. Do it. Now the candle is giving off so much thermal energy that the wax is absorbing it and melting. You can see the thermal energy. And it's also giving off like heat and stuff. And that's experiment 1. Oh! And welcome to the next experiment. In this experiment, we'll be using fire and ice. Okay, what we'll be doing is using the specific heat index of the ice to raise its temperature to the ice's melting point. Yes, fun stuff. For this experiment, I will be needing some ice. Mr. Ragely, the ice. Mr. Ragely, the ice. The ice, Mr. Ragely. Hey. Ice! Thank you, Mr. Ragely. As well as the ice, I will be needing ice extracting device. Mr. Ragely, an ice extracting device. Mr. Ragely, the ice extracting device. Get it talks. Thank you very much. Okay, here we go. I'm extracting the ice from its Super Duty holding cell, and I'm holding it over the flame.
This is actual ice and a real candle. Do not attempt this at home. I repeat, do not melt ice.
Now you see, heat is the flow of energy due to difference in temperature. And there is a great difference in temperature between the ice and the flame. So the heat from the flame is flowing into the ice. You see, it's melting. Thereby changing the state of the ice from a solid to a liquid. That is experiment 2. Hello! And now it's time for our third and final and most exciting experiment. I will show you thermodynamics by using a steam engine. The heat creates movement. Unfortunately, I
don't have a steam engine, so, instead, I will show you friction, where movement creates heat. Here we go. Warm. That's right, it's warm, because the friction created heat. Now I will show you how friction creates heat another way, by using matches. Mr. Rangeley, the matches, please. Mr. Rangeley, the matches. Mr. Rangeley, the matches. Matches. Thank you, Mr. Rangeley. Now, here we have everyday kitchen matches. Right. What happens is, you rub them against the perforated surface, and what are you doing? And the friction causes the chemical reaction to take place, which causes a flame. Watch. Oh, there's the flame! Thermal energy caused by friction, ladies and gentlemen, right there. Perfect example. That is the end of the final experiment. Oh, hello! When did you get here? I hope you've enjoyed this educational programming in physics and thermal energy. We've spent countless hours on it and several people have died during the making of it. And there are several people we'd like to thank. Our first being our cameraman, Mr. Andrew Rittenauer.
Hello, Joe!
Yes, hello. The next being Mr. Joey Storr as Dr. Farget Marv. Why, thank you. I enjoyed it very much. And finally, Mr. Ben Pagels as Mr. Blah Rangeley. Where's Ben? Where'd he go? What's he? Oh, hey, there you are! What you got there? Ice skate? Ah, well, I'll just be getting out of your way then. Yeah, that's Now!
Welcome to Bowling with Physics.
See me right out of that sunset on your color TV screen. For all that I can get, if you know what I mean. Women to the left of me and women to the right. Got no gun, got no knife, don't you start no fight. 'Cause I'm TNT, I'm dynamite, TNT.
We're going to be measuring this bowling alley lane from behind the pins to this line right here. We're going to do it in 12-foot increments due to the fact that this is the only tape measure that we can find.
We got it.
1 minute.
We got it right here.
Yeah, we got it at Howard's.
Go to Howard's.
So lock up your daughters, lock up your wife, lock up your back door and run for your life. The man is back in town, so don't you mess me around. 'Cause I'm TNT, I'm dynamite, TNT. And I win the fight, TNT. I'm a power low, TNT. Just watch me explode. I'm dynamite, TNT. And I win the fight, TNT. I'm a power low.
Observations and measurements that the length of the bowling alley is 65 feet.
Yes.
And that is the length we'll be using in our equations to find the velocity of a bowling ball. The length of the bowling alley.
Knuckles are white and my face is bright red. Road rage. Doing 65 on a souped up moped. Road rage. Is that you that gave me the finger? Road rage. How come you won't turn off your blinker? You shouldn't drive like that. I got a baseball bat. You're gonna get it. You're gonna get it. Roll down your window.
We analyzed our findings and we recorded the time it took for each person's bowling ball to get down the lane. And we used this equation here. We will have our lovely cameraman zoom in on it. V equals d over t, which is the velocity equals the distance divided by the time. And by taking each person's time on this lovely Howard's receipt, we have our very accurate findings. And by using significant digits in our division, we concluded that Jeff threw the bowling ball at 20, with a significant digit sign over the 0, 20 feet per second. Devin throws a bowling ball at 15 feet per second. Elizabeth throws a bowling ball at 14 feet per second. And Holly throws a bowling ball at 15 feet per second, and I throw a bowling ball at 16 feet per second. Thank you for watching.
Take my hand and come with me because you look so fine that I really want to make you mine. I say you look so fine that I really want to make you mine. 4, 5, 6, come on and get your kicks. Now you don't need the money when you look like that, do you, honey? Big black boots, long brown hair. She's so sweet with her get back stare. Well, I can see you home with me.
Good grief, man. It's only an 8-pound ball.
I know it's an 8-pound ball. Give me a break.
Because you look so fine that I really want to make you mine. I say you look so fine that I really want to make you mine.
Up, Devin, $30 for the
Come on and
break.
get your kicks. Now you don't need money with a face like that, do ya? Big black boots, long brown hair. She's so sweet with her get back stare. Well, I can see you home with me, but you were with another man. Yeah, I know we ain't got much to say before I let you go.
Everybody up on your feet.
I don't mind coming here today, Josh. Wasting all my time. Cause when you're standing oh so near, I kinda lose my mind. It's not the perfume that you wear, it's not the ribbons in your hair. And I don't mind you coming here and wasting all my time.
Ready to film this now? Think on it.
I know what I'm good at, because I'm the last one.
All down at Margie's bar, telling stories if we had one. Someone fired the old jukebox up. The song it sure was a sad one. A teardrop rolled down Bubba's nose from the pain the song was inflicting. And all at once he jumped to his feet, just like somebody kicked him. Bubba shot the jukebox last night. Said it played a sad song that made him cry.
This is the moment we've all been waiting for. Let's get ready to rumble!
Miller. And now, here, we are doing practical demonstration in physics. What is physics? Well, I don't know. But we're going to be doing some experiments to warp your mind. Our first experiment will be with roller skates, demonstrating Newton's first law, which is an object at rest is to stay at rest until acted upon by an outside force. Then the object is moving, does not rest. To demonstrate this, here is a roller skate. It is at rest. Watch it now. Watch it. It stays at rest. Now, when it's acted upon by an outside force, it moves. When it stops, it's gravity and friction that stopped it. Now we will experiment with a cat. We'll have a motor dual car pull in reverse until the cat falls off. Momentum stopping the vehicle will throw the pussy off. Now, two experiments. First, the gun will show inertia, and the bow now will show potential energy and momentum. Go. No, hold on. Okay. Now, force. The force of the gun, when shooting it, is not greater than the force of the man. Therefore, the gun has less inertia than a man. There is a force in the shoulder when the gun kicks back, but it's not significant because mass is greater than mass. So this experiment is showing potential and kinetic energy and the transfer thereof. When the man pulls back the arrow, it is in potential energy. When he releases it, the arrow propels forward and transferring it from potential to kinetic energy, giving it momentum. And here's a word from our sponsors. Brought to you by Mr. Nash, eating his ice cream. Delicious ice cream, that is. Hi, I'm Troy McClure. I'm from Kitty Killer's Extermination Company. Are you tired of your cat? Pat Kitty, you done worthless cat? Then call 555-DEAD.
Everybody was kung fu fighting. Those kids were fast as lightning. In fact, it was a little bit frightening, but they fought with expert timing.
Our next experiment will involve a potato gun, which the pressure builds up inside is ignited and propels the potato into the air. The other one, look what's been doing, wheeling a golf ball. As the swing goes back and comes forward, it will hit the golf ball, which is at rest, and propel it into the air. Got it.
Yeah, yeah. Born to be wild. Born to be wild.
And now, the conclusion. What have we learned today? Well, I'll leave that up to you. Now time to introduce myself and real. I'm Jack Cotton. Here are my co-stars, Terry Howard